In this lecture, we give introduction to Mashke's theorem. So let us start with the definition. So let V be a vector space and say this U is a subspace of vector space V. So we call another subspace W of V. So this W is called complementary to the subspace U. If you take U plus W generates the entire vector space V, and the intersection of these two subspaces is just 0. So in fact, in this case, V is actually a direct sum of U and W. So this is a V is isomorphic to this direct sum. So we can immediately show this. So you have this map from here to here, which is given as some element U plus W, which will get mapped to V. So this map is on towards the surjective, since you have this equality here from here, and it is injective or N2, since U plus W, if it is mapping to 0, then that would imply U is equal to minus W, which lies in U intersection V. But U intersection V is always 0, so it has to be the case that U and W are 0. So you can see, if you have this complementary subspaces like this, we can write V as a direct sum like this. So now say we are given two representations, one like this and one like this. Then we can define a new representation on this direct sum, say sigma, which with maps you're just taking the representations like this and like this. So basically just this comes here, this comes here, nothing else. So sigma is just this. So in terms of matrices, what we are trying to do is that if this corresponds to a matrix, this corresponds to a matrix, then we are talking about block diagonal matrices. So these were the two matrices which corresponds to, so this A say corresponds to row of G, B corresponds to row prime of G. So then such a representation will look like a block diagonal matrix. So a block diagonal matrix, and it will obviously act on these vector spaces V and V prime. So nothing deep, just standard linear algebra. So now we come to another definition. So a representation is decomposable if it is isomorphic to direct sum of two representations of smaller dimension. So V is iso to U plus W, with U and W non-zero. So this is the way we write it. So we are talking about decomposable now. So now let us see the interplay between irreducible and decomposable. So the first result is that irreducible implies indecomposable. So what we are going to use is, to prove this is contrapositive, so we are going to use prove that decomposable implies reducible. So suppose V decomposes as W1 direct sum with W2. So this is what decomposition looks like. So then you can take the image of this map, W1 going into W1 direct sum with W2 to V. So this now W1 is non-trivial. So this is a proper sub-representation of V. So image of W1 via this map is a proper sub-representation of V, making V reducible, because image, as we have seen, is a sub-representation. We gave an example that image is sub-representation, and now we are saying this W1 is embedding into V as an image, so it has to be a sub-representation, and this W1 is non-zero precisely because we are decomposing here. So in decomposition you have non-zero. Now we come to the statement of Mashke's theorem. So let G be a finite group and V as the representation, and say we have a sub-representation U. So then there exists another sub-representation W, and this W is complementary to U, and this gives us, the theorem says that you can find such a representation W. So if you're given a sub-representation U, you can find a complementary sub-representation W, and then you can write V as U direct sum with W. So again, you're given a sub-representation, then you can find a complementary sub-representation and write this. Now, so the big part of the theorem is not to find the complementary sub-representation, that is fine. The big part is to actually prove the G invariance. So let us make a remark first. So say G is a finite group. What if G is an infinite group? Does the theorem hold? Actually, the theorem does not hold. Let us give an example of it. So this theorem actually fails for infinite groups. So for example, if a group is integers and your vector space is this complex 2. So we can say to 0 you obviously have to attach an identity matrix, and row of 1 is some matrix M. So this matrix M we are actually writing like this. So this is the matrix here, and this is an invertible linear map. So we immediately see that what is row of 2? This is row of 1 plus 1, which has to be row of 1 times row of 1, so M square. And inductively row of n is mn. You can actually keep on multiplying the matrices and you will see you will get something like this. So n here. So what we only need is row of 1 to determine rest of the matrices, which will take C2 to C2. So we are obviously finding matrices which go from here to here. So we obviously have a one-dimensional sub-representation, which is just complex C10. So this just bases like this, but there is no Z stable subspace of C2 complementary to U, because Mashke's theorem says that you have this sub-representation, then you should be able to find something W so that you can write your space like this. But we are saying this W does not exist, because if rho is decomposable, it would be equivalent to a direct sum of one-dimensional representations, because this is one-dimensional representation, so the other one also has to be one-dimensional, and such a representation would have to be diagonal. So that means this M has to be a diagonal matrix. This has to be a diagonal matrix, but you can use linear algebra to show that M is not diagonalizable. So the Mashke's theorem or Mashke's theorem does not apply to infinite groups. So let us discuss two corollaries of Mashke's theorem. So the first corollary is indecomposable representation of a finite group G is irreducible. So here we see that irreducible is implying indecomposable. Here we are saying that indecomposable is implying irreducible, so opposite direction. So compare these two. So again we are going to use contrapositive, so that is we are going to say that V is reducible, and that would imply decomposable. So V is reducible, so that means it has a sub-representation U, and then by Mashke's theorem we basically mean that we can write V as U direct sum with W. So that means V is decomposable, and that's what we wanted to show. So corollary 2 is complete reducibility. So say G is a finite group with some representation, this rho V. So then this V you can write it as this direct sum of W1, W2, W3 all the way to say some WR direct sum, where each of these Wi are irreducible. So we are going to prove this using induction on dimension of V. So you induct on the dimension of V. So one-dimensional representation is irreducible. So for n equals to 1 it holds, and suppose it holds for all dimension which is less than n. So let dimension of V be n, and suppose every representation of dimension less than n is isomorphic to a direct sum of irreducible representations. So if dimension is less than n, so it is isomorphic. So now we come to the proof after our inductive hypothesis. So if V is irreducible, we are done, nothing else to be done, because that's what we wanted to show. Now if it is not irreducible, that means it has a proper sub representation U of V. Now Mashke's theorem says that you can find a complementary space W and you can write it like this. So by the theorem we have V is this. So this is coming from here. But now both U and W will have dimension less than n. And now by our inductive hypothesis, both of them have to be a direct sum of irreducible representations. So because that's what we supposed here, the dimension less than n, it has to be direct sum of irreducible representations. So by inductive hypothesis, each of them breaks down into direct sum of irreducible representations, which implies V also has irreducible representations, because then V is just direct sum of irreducible representations here and the direct sum of irreducible representations here. So something like this we will get. So now we will prove Mashke's theorem in the next lecture.